Okay, so we're going to get started. Welcome to the last day of the workshop. And our first speaker in the morning session, the only session today, is Nicole, who's going to tell us about shortest path structure in graphs and need for line simplification.
Hi, everybody. Thank you for coming. So I'm going to be talking about some joint work with Bernstein and Greg Bodwin. And we're going to be talking about answering the question of, are there graphs whose shortest path structure requires large edge weights? So let me tell you what I mean by that next. So this is a talk about graph simplification. And I guess most of this week has been focused on graph sparsification. This one is not about sparsification. It's about trying to take large edge weights and make them smaller, I guess kind of similar in spirit to Sepper's open problem from yesterday. So what are we doing here? So here's just a list of like a few other graph simplification problems. Like these two are the classic kind of sparsification problems where like spanners or sparsifiers where you're trying to, preserve approximate shortest paths or flow cut or any number of other things. I want to throw in one other example, which I don't think has been talked about this week, although I wasn't here for every day, which is shortcut sets and hop sets, where the simplification that we're trying to do is to reduce the diameter of the graph as much as possible by adding extra edges and preserving reachability or shortest paths. So I'm not going to be talking about that, but this is about shortest path problems. So I'll tell you what I am going to be talking about, which is like a new problem that we're introducing in this work. And it is the following. So what we're trying to minimize here is aspect ratio. That is the ratio of the largest edge weight to the smallest edge weight in the graph. And what we're trying to minimize, that's what we're trying to minimize. What we're trying to preserve is the shortest path structure. So more specifically, here's the actual definition of the problem. And this, as far as I know, it was first studied in this work. So again, the aspect ratio is the ratio of the largest edge weight to the smallest edge weight. And what is our input here? We have a positive weighted graph, G. It could be either directed or undirected. And the weights could be anything. They could be exponentially large or whatever. So it has arbitrary aspect ratio. And what we would like to do is to reweight the graph in order to have small aspect ratio. We're not going to be changing the graph at all. The graph structure, all of the edges are going to stay exactly the same. All we're allowed to do is to change the weights in order to form a graph H, same as the original graph, just new weights, so that the aspect ratio is minimized. And this is the thing we're trying to preserve. For all vertices, S and T, if P is a shortest path in the original graph, then P is also a shortest path in our newly weighted graph H, and vice versa. That is to say, if there exists a shortest path from S to T that goes through this particular sequence of vertices, V1, V2, V3, etc., then that particular shortest path is also a shortest path, that sequence of vertices in the new graph. The shortest path is not going to have the same weight as it did originally because we reweighted all the edges, but it is going to be, we insist that the sequence of vertices that we're going through is the same. Does the problem definition make sense? Any questions? No, and in fact, a lot of our results are lower bounds.
Yes. Is it like more of an existential question or addition to algorithms that we're studying here?
Good question. So this is an existential question. So the question we're trying to answer is, we want to make statements of the form, for all graphs, there exists a way to reweight the edges down to aspect ratio, blah, while preserving all the shortest paths. Or there exists a graph such that that's not possible.
Maybe this is a better question for Jen, but is there interest in like some kind of approximation of this?
Yeah, so we study at least one notion of approximation of this. And I don't know which one you have in mind, but yes, I will get there. Good. Okay, so here's an example just to make sure the problem definition is clear. Let's say this is our original graph. The aspect ratio is 500/5, so 100. Now, here's our reweighting. We reweighted all of the edges in the graph down to aspect ratio 4. And now you'll notice, if I did this right, if you check for every single pair of vertices in the graph, the shortest path should go through the same sequence of vertices. So for example, from here to here, the shortest path goes like this, up and down. In the new graph, we can check that indeed the shortest path from here to here does still go up and down. So that's good for that pair at least. Sound good? Yeah.
So the aspect ratio doesn't say anything about the variance of like the edge weights. Would that actually come up somewhere in this?
Yeah, that's right. So there's nothing about, in this problem, nothing about like the distribution of edge weights or anything. We're just talking about the max and the min. There might be some interesting questions with the distribution or something, but we don't study it in this work.
So after reweighting, it's possible that an edge that was originally the cheapest in the graph is no longer the cheapest, right? For instance, you could have reweighted the 53 to 1 and the 5 to 2, and I think you'd still have the same.
Yeah, that's right. So there's no kind of requirement that the relative weights of the edges has to stay consistent. Okay, so now let me tell you some maybe motivation. I mean, I think this is kind of a nice question on its own, but maybe if we could answer this question, what might we want to do with the answer? And let me tell you up front that all of this is completely hypothetical. We have results on this problem, but we don't know of any particular concrete applications to something else. So that's an open question here. So what to do with the answer? Here's the question. Is it always possible to reweight a graph to bounded aspect ratio? Let's say bounded here means like polynomial aspect ratio, while preserving the structure of shortest paths. If the answer were yes, then we might try to do something like the following. We might like sort of use the reweighting as a pre-processing step in some algorithm in order to get rid of a factor of log aspect ratio in the running time of the algorithm. So in particular for shortest paths especially, many algorithms have some dependence on the aspect ratio. Oftentimes it's log aspect ratio, so especially shortest paths in like the dynamic settings and distributed and parallel and other settings. There's oftentimes a log W factor because they're doing some kind of bucketing of the weights, etc. And what you might hope to do here is to say, okay, we take our graph with arbitrary aspect ratio, reweight it down to polynomial aspect ratio. If we can do that quickly, then we could just run our original algorithm on our newly weighted graph in order to change this log aspect ratio to like a log n factor, let's say. That would be kind of the goal if we could answer the question positively in this way. On the other hand, if the answer were no, you might try to do something like the following. So we want to kind of use the fact that bounded aspect ratio graphs do not capture all possible shortest path structures to get better algorithms for graphs that have bounded aspect ratio. So let me tell you what I mean by that, which is that like many theorem statements or some theorem statements at least have the structure of like, assume that the graph already has polynomial aspect ratio, then blah, blah, blah theorem statement. And what you might hope to do here is to say, well, look, if not all graphs can be reweighted down to polynomial aspect ratio, that means that it's only a particular structure of shortest paths that are present in that graph. And so if you're trying to get theorems about graphs with bounded aspect ratio, it turns out that they have a particular structure that maybe you could, take advantage of in your algorithm. Any questions? So again, this is all hypothetical. And now let me tell you kind of concretely what we know about this problem. Yes?
Reduce the aspect ratio. The dependence was on log anyway.
So yes. So here the question I'm trying to ask is like, is it always possible to, given a graph with any aspect ratio, always reduce it down so at the end you have polynomial aspect ratio?
Nice.
Okay. So let me first tell you to kind of get calibrated to the results we might expect for this problem of a simple lower bound of omega n. That is to say, we can't hope to get anything better than omega n aspect ratio. And here's the lower bound. It looks like this. So like you have a graph that's just a path on n vertices and n minus 1 edges of weight 1. And then you have this one big edge going over the top of weight n. And the point is that in this graph, you'll notice that the shortest path from the beginning to the end goes like this through all of these edges. And so if I decide to reweight this graph to try to achieve lower aspect ratio, what would I do? Well, I would say, okay, I need to make sure that this is still a shortest path in my newly weighted graph. And specifically, let's assume that in my newly weighted graph, the lowest weight is 1, just kind of, I can assume without loss of generality by scaling. So lowest weight is 1, which means that all of these weights in my newly weighted graph have to be at least 1. And therefore, the length of this path is at least n minus 1. And so if I want to make sure that this remains the shortest path, I'm not allowed to reweight that big edge down to anything lower than n minus 1. Does that make sense? Okay, so this is kind of our baseline of the best thing that we could hope for is linear. This is just a reminder of the problem down there. Okay, so now let me tell you, yeah. So in this problem, we're assuming that the original graph is positive weighted and our new graph is also positive weighted. There might be interesting questions for negative edge weights. I'm not sure, like there are known results like with Johnson's algorithm for APSP that you can take the negative edge weights and use some price function to like make them positive. So there might be some reduction there. But here we're just focusing on positive.
Just so that I understand, if all you're aiming for is the poly-n bounded like aspect ratio, can you just assume your graph is always has all the edges?
So can you assume your graph has all the edges? Because the missing edges, you could assume they just exist, but they have super, super large weight. Yeah, you could assume that.
So here, the n-weight edge doesn't participate in any shortest path. Right?
That's right.
We just ignore all these edges.
Yes. Yeah, that's right. So it turns out that no, that like you can construct examples where all of the edges participate in shortest paths and you still get a lower bound like this. Okay, so here is what we discovered about this problem. So we're asking the question of, is like linear or polynomial aspect ratio always possible? And we study DAGs, general directed graphs, and general undirected graphs. And it turns out the answers to these questions are yes, no, and no. So in particular, the results that we can get are, for DAGs, it turns out you can match the upper bound of order n. But then immediately when you add cycles to your graph and you have undirected or directed graphs, you immediately lose and like you get this huge lower bound of 2 to the omega n. So that is to say there exist graphs such that no matter how you reweight them to preserve the shortest paths, you're going to still end up with aspect ratio exponential like this. And then we also study like the approximate version, which I'll come back to a little bit in the end to define kind of what do I actually mean by that.
The second two parts, does it mean the original graph should have had also weight around 2 to the omega n and you cannot make it better?
Yeah, like the requirement would be that in the original graph, the aspect ratio is at least that and we can't make it better. So today I would like, actually first I want to tell you kind of out of order, a couple of open problems because I thought they're maybe good to have in mind while I talk about the results. So here's one concrete open problem we don't know the answer to. What if you care about DAGs that have edge weights from 1 to W and they're all integers? You'll notice when I tell you about the DAG one here that the edge weights are very much not from 1 to W and all integers. And if you could actually show an upper bound for this and do it efficiently, then this would imply it would actually have like some application to a concrete problem. And we don't know what the answer to this one is. And then another question, of course, is like getting applications for these things or finding relations to other problems. Yeah, like it would still capture, like we still don't, I guess the main, if we assume the graph has integer weights initially, that's kind of the main question that I want to answer, yes.
Didn't get on this last question, the DAG question.
Yeah, so we want to reweight so that you get a so that your final graph is a DAG where all of the edges are integers between 1 and W. In the one that I'll show up here, all of the edges are not necessarily integers. So I guess you can make them integers if you make them big enough. But if you scale them down to be between 1 and W, they're not integers.
So you started with an integer weight, you create some real weights, but the aspect ratio is smaller. It's the
Yes, yes, that's right.
You mean you want the result to depend on W, the aspect ratio?
Okay, so here W is just a weight. Like, okay, so W is the aspect ratio here because the lowest weight is 1. But let's say the aspect ratio of the original graph is arbitrary, and then what I'm trying to do is reweight down to integer weights between 1 and some polynomial or some linear. I see that was confusing. So I want this W to be like some small number, like polynomial or linear.
W is the target weight.
Yeah, sorry, thank you. W is the target weight. Thank you.
So can we do better if we assume that there's maybe a polynomial number of shortest paths between every pair of vertices, or?
Good. So in our lower bound that I'll show you, there's one unique shortest path between every pair of vertices. Good question. Okay, so today I'll show you both of these two things. I won't talk about this one. These two things are actually both very kind of nice and simple, and I can actually tell them to you. So let's go. So let me show you the upper bound for DAG. So this is a linear upper bound for DAGs. For every DAG, I can reweight its edges down to linear aspect ratio and preserve the shortest path structure. So here's what we're going to do. The first observation is that we are allowed to take any vertex and do the following transformation to it. Take all of its incoming edges and add x to them for some value of x, and take all of the outgoing edges and subtract x. And the observation is that this doesn't change any of the shortest path structures. In particular, if you have a path that's going through this vertex, you'll notice that the weight of the shortest path does not change because you get plus x minus x. On the other hand, if you have a shortest path that starts or ends, let's say it starts at this vertex, you'll notice that all of the shortest paths starting at this vertex are decreasing themselves by minus x. And so all of them decrease by the same amount. So even though the weight of the shortest path changes, the actual shortest path, the sequence of vertices, does not change because I'm decreasing them all by the same amount. The one that used to be shortest is still shortest. Does that make sense?
Or are you just reducing all the edge weights by the same?
Yeah, so the transformation is I pick an arbitrary vertex, I take all of the incoming edges, I pick an arbitrary vertex, I pick any x that I want, I take all of the incoming edges to my vertex, do plus x to them, the original weight plus x, and then here the original weight minus x for the outgoing ones.
This is true even for general order.
Yes, so far we haven't used the fact that the graph is a DAG. And this is an application of price functions in case you've heard of those. If not, that's fine. Okay, so let's assume that initially all of the edge weights are between 1 and W. So sorry, this is a different use of W than before. Initially, all the edge weights are between 1 and W. And then what are we doing? So W could be large, it could be exponentially large here. What is our algorithm? First, we take the topological order. This is where we're using that it's a DAG. We take the topological order, and then we go through the order and apply this transformation with x equal to W times I for the ith vertex. So you take the first vertex, you do apply the transformation with W. Second vertex, 2W, third vertex, 3W, fourth vertex, 4W, and so on. Make sense? So now I need to argue to you that the aspect ratio is now low and something around linear. And here's why. So we can say, look, well, what happens to a single edge in this graph? So let's look at a single edge. We're going from vertex I to vertex j. This is the ith vertex in the topological order to the jth vertex in the topological order. And what are we saying here? We're saying, well, look, how did this edge change? Well, when we did the transformation for I, what did we do? We subtracted I times W from this edge by our definition of this algorithm. And then when we did the transformation for j, we added w times j to this edge. And so on net, this edge is changing. It's increasing by plus w times j minus I, where j and I, again, are the indices of those vertices in the topological order. Okay, so now we can say, well, look, what is the minimum edge weight here? It's at least w, because what did we do? We added at least w to every single edge, because this j minus I is at least 1. So we added at least w to every single edge, minimum edge weight at least w. And then on the other hand, what's the maximum edge weight? Well, I claim that it's at most first w, because the original graph had max weight w. And then what did we do? We added at most w times n minus 1 to that one, because this j minus I is at most n minus 1. And so now you can see that the ratio between these two things is like n. So this comes back kind of to Sepper's question. You'll notice that the weights on this graph are integers, but they're very large. And so if you scaled them all down to be between 1 and something, they're not going to be integers. Questions here? So I view this as kind of a, I guess, preliminary result for this paper. Now let me tell you something about the lower bounds. So, this construction turns out to also be rather simple, even though kind of we started off with a more complicated one, and then in the end, there is a simple construction realizing this. So we're trying to do a directed lower bound that's 2 to the omega n. So here's what we're going to do. This is what the graph looks like. So we have a directed triangle that's clockwise on the top. The next one is counterclockwise, then clockwise, then counterclockwise, alternating. And there are going to be n over 3 of these triangles. And then then there's a bunch of like matching edges in between them, and they all point downwards. And this is the entire graph of the lower bound. And I've already decided what I'm going to dress up as for Halloween next year. Okay, so I now need to tell you about what the edge weights are on this graph, and they are the following. So the edge weights on the first triangle are 1, the next one are 1/3, next one 1 over 3 squared, 1 over 3 cubed, etc., down to 1 over 3 to the power of n over 3. And you'll notice that the aspect ratio of this graph is exponential. It's 3 to the power of n over 3. And now we need to argue that indeed you can't like decrease the weights while preserving the shortest paths down to anything below this exponential. So here's how the argument works, and it's really kind of quite simple. By the way, these down edges are all, we're going to say they're all weight 0. It really doesn't matter. I could actually weight these downwards edges anything as long as they're all the same, so let's just pretend they're 0. Okay, so, I mean, then the aspect, yeah, that's fine. If the aspect ratio of the original graph is infinity, that's fine. Okay, so here's what we're going to do. We have 2 vertices here, one from the top triangle, one for the next one. And then we're going to say, well, what is the shortest path between these two? And if you look at this for a few seconds, you'll realize that the shortest path between these two is the following. It's going to take one of these down edges, that's 0. Then it's going to take 2 of these triangle edges for 2/3. And that's the only shortest path between this pair. And then we can also ask ourselves, it's going to be useful to talk about what is not a shortest path between the same pair of endpoints, and it's going to be this. So this is one example of not a shortest path between these 2 edge points. It's only on 2 edges, which is the significant part here, is that we have a not shortest path that's on fewer edges. We use this one edge, which costs 1, and then a 0 edge. So this is a not shortest path of weight 1 and a yes shortest path of weight 2/3. And the point is that you can do this for like any pair, like the whole graph is symmetrical. Like I could, instead of choosing these 2, there's like a matching. I could choose, you know, like these 2 and these 2. I might have done that backwards, but there's a matching between the bottom, this triangle and this triangle of 3 pairs of vertices where you get the exact same phenomenon happening. Make sense so far? Okay, so Now what we can say, this is like the useful part, we can say that, look, well, in the final graph, we need it to be the case that this path remains a shortest path. This particular sequence of vertices remains a shortest path. And so what can we say? Well, we can say that means the sum of, like if you take all three of those matching pairs, the sum of all of those shortest paths has to be less than the weight of the sum of all of those not shortest paths. And if you do that, you get the following thing. You get that like the blue triangle on the top, this one, its weight has to be at least twice of the second red triangle here. Because when we add up all of those not shortest paths, we're using each of these edges once. And on the other hand, when we add up all of the yes shortest paths, we get like this, and then we get this, and then we get each pair of two. And so we cover that whole triangle twice. And so the point is that what we've shown is that the weight after reweighting of the blue one is at least twice, of the top one is at least twice that of the next one. And this graph is just the same thing for n over 3 layers. And so you can do the same exact argument for all of the layers and say, well, okay, the weight of this one is at least twice that of this one, which is at least twice that of this one, which is at least twice that of this one, et cetera. And so then you get that the aspect ratio becomes exponential.
So what happens if you just set the dotted edges to arbitrarily to something like 100? They don't really change the shortest path, right? You can just blow them up to some 100 or something, and then that gives you.
So are you asking about like these vertical edges?
The dotted yellow color.
Oh, like this one too? Yeah. So if I put this one up to like 100, so here's the issue with that, is that you could imagine that instead of this shortest path, we would have a shortest path that looks like, okay, I think you're right that in the top layer you could increase them to as much as you want, but as soon as you get to the next layer, okay, so I guess your question is, can you increase them as much as you want? Yes.
My idea is to increase the right layer to a big value, so that then the people who are down below can also be increased to kind of like to increase by some extent. They no longer need to be 1 by 3 power i's. They can probably, hopefully, I mean, I'm sure I'm wrong, but I'm thinking maybe you can make it 1 by 3 power 2 or something instead of 3 power I, and then the aspect ratio would hopefully not be so bad. That's just.
Yeah, so I think your idea, like if you take all of them and scale them up, you should get the same phenomenon happening. Like you should still get the case, you should still get it that the top triangle has to be at least twice the next triangle. And you'll kind of scale everything up and you'll still get exponential. But we can talk more about it offline. Okay, so any other questions? Yeah.
Yeah, you need how many different sets of weights do you need, like logarithmically maybe?
Well, here we're doubling each time for n over 3 times. So we're having like linear and different weights.
Yeah, I was wondering, like, if I promise you that I only have like t classes of weights in the graph, is that log 1 actually saying like, oh, you need exponential in t?
That's a good. Oh, does it?
Like a positive result saying, okay, in the worst case that's going to be 2 to the n, but actually, if I know that I only have 3 types of weights,
then can you do better? Yeah. I see. Yeah, that's a good question. We didn't think about it. I think you could probably do something by like, yeah, I'm not sure. I would have to think about it. You might be able to make some of these cycles bigger at some point, make the edges the same, and then like jump back down to the smaller one. I'm not sure how much that would buy you though, so good question. Okay, I think I'm out of time here. So the approximate version, this is just kind of the definitions of the approximate version, which I won't explain because they take a little bit of time. If you're interested, we can talk more offline. And the basic results of the approximate version are like, even if you kind of relax this problem just a little bit, like, even if I try to make this problem a little bit easier for general graphs, it's like I still can't get anything. I still get like exponential bounds. And on the other hand, if I try to make the problem even just a little bit harder for DAGs, then I immediately jump up to an exponential bound. So there's kind of negative results for kind of different relaxations and generalizations of the problem. Here's the result statement again, and I'll stop here. Thanks everyone for being here.
Is there an upper bound also that's like 2 to the lower band, or is it more like n to the can choose 2 or something? Or
Yeah, so I've given this talk a few times, and this is a common question, and I believe there are some people thought about it afterwards. We don't have it in this paper, and they were able to get something. So people might be like actively kind of working on this right now, but I'm pretty sure that they were able to like get something at least similar to the upper bound. Good question. Yes.
And it claims about some special class of graphs, planar graphs or...
Yeah, good question. So let's see. This is a very simple graph, and is it planar?
It's planar.
Okay, I believe hung. It's planar. So, yeah, unfortunately.
Because you can embed on a cylinder.
Any other questions? Okay, so let's thank Nicole again.